Scaling a large language model in production is currently governed by one factor: the physical limits of a GPU's memory. This diagram represents the 80 gigabyte capacity of an enterprise GPU. Running Llama 3 70B with a 128K context requires 45 gigabytes of VRAM just for the attention state. And this 45 gigabyte requirement is consumed by each individual user session, independent of loading the model weights. On an NVIDIA H100, this requirement creates a hard ceiling. It limits the number of concurrent requests a server can host before the hardware is exhausted. While academic research has produced quantization algorithms to compress this data, these prototypes often lack the lifecycle management needed to prevent memory fragmentation at fleet scale. Inference economics are determined by memory orchestration. Success in this domain depends on how efficiently a system can manage these massive transient data structures. Most machine learning papers provide raw algorithms. They rarely include the production infrastructure required to manage state across thousands of sessions. Managing state for 100,000 concurrent contexts using standard software memory allocation causes performance degradation through fragmentation and garbage collection pauses. KVin is a GPU-native orchestration layer designed to sit between the inference engine and the physical hardware memory. The engine consists of 8,114 lines of C++ and CUDA code. It drives 3 custom kernels, including a fused dequantize and attend kernel that eliminates intermediate staging buffers. It utilizes a 3-level radix tree for position lookups, maintaining a speed of 1 to 2 nanoseconds, even as the context grows to 128,000 tokens. This radix tree provides a constant lookup time, avoiding the linear scans and unbounded delays found in many research implementations. Treating KV cache compression as a high-throughput systems engineering problem allows for the stability and speed required for production serving. The architecture of KVin originates from a system developed over 2 decades ago. In 2001, financial streaming platforms were required to process millions of market events per second with sub-microsecond latency and absolute reliability. The engineering profile of an LLM KV cache is nearly identical to that of a financial streaming cache. Both systems manage data that is append-only, time-indexed, and requires real-time querying across multiple levels of precision. KVin maps these historical components directly to the GPU. The original message bus is now the KVin bus. The task tick memory allocator becomes the KVin arena bump pointer allocator, and the task sec map indexing logic provides the basis for instantaneous sequence lookups. Translating a research paper into a production system requires building complex memory lifecycle logic from scratch. KVin provides this orchestration layer as a hardened existing framework. This architectural lineage provides the system with a level of operational stability usually reserved for mission-critical financial software. The system was benchmarked on an NVIDIA H100 GPU to measure its impact on large-scale model serving. Testing on Llama 3 70B with a 128K context window showed a deterministic compression ratio of 3.67 to 1. This ratio results in 30.5 gigabytes of VRAM saved for every user session. This effectively frees up 38% of an H100's total memory capacity. These savings allow a single GPU to host 3 to 4 times more concurrent sessions at full context length. The compression is achieved while maintaining the model's attention patterns and overall fidelity. KVin uses per-head adaptive precision. It calculates the Shannon entropy of each attention head in real time and automatically assigns 2-bit or 4-bit precision based on the data's complexity. In local tests using the Qwen 3 30 billion parameter model, 52% of the heads were automatically compressed to 2-bit without any manual tuning. Because larger models have more layers to distribute fixed overhead, the benefits of the system increase as the model size grows. KVin converts unpredictable transformer state into a deterministically managed compressed memory asset. KVin is packaged as a complete operational stack, ready for immediate deployment into inference clusters. The engine includes 89 passing C++ tests, covering every component from arena allocation to the full quantization pipeline. It ships with an observability suite featuring a live dashboard, real-time compression metrics, and an MQTT telemetry feed for fleet-wide monitoring. For existing VLLM deployments, KVin acts as a drop-in cache engine replacement. Activating the backend requires 2 lines of Python code. The technology is ready for enterprise environments, with Docker images and Helm charts prepared for Kubernetes GPU clusters. Utilizing a hardened infrastructure layer eliminates the significant risks and engineering delays associated with building custom memory management from scratch. Infrastructure directors must now decide whether to build their own KV cache compression or adopt an existing solution. Internal development of a similar orchestration system requires a dedicated team of GPU engineers and months of research and development runway. Licensing KVin provides a functional, production-ready architecture that is available for deployment today. This system is specifically designed for inference companies aiming to scale to 100,000 or more concurrent contexts. There are 3 primary deal structures available: a full acquihire to bring the technology and its developer in-house, or a technology license for internal integration, and a consulting option for custom environment setups. Large-scale inference platforms are actively moving toward integrated KV cache compression to remain competitive. With the benchmarks confirmed and the integration ready, the system is now available for adoption by teams seeking to maximize their GPU efficiency.